Am I mic'd? Yep. Hello, everybody. Thank you all very much for coming. I'm Bob Strachan. I'm a senior consultant with the Public Sector Professional Services Group here at AWS. And it's my honor today to share this session with Dr. Taha Kashout. Taha is a practicing cardiologist. He's also a technologist, the first Chief Health Informatics Officer at the FDA and creator of the award-winning Open FDA platform. He is also a strategic advisor to the American Heart Association, and it's in that capacity that he'll talk to us today about the precision medicine platform from the AHA. Okay, is my clicker not working? I'm going back. Okay. All right. So the title of our talk today is Harmonize, Search and Analyze Scientific Datasets on AWS. It's all about creating opportunities for your researchers and data scientists to uncover and share new insights. We split the session into two parts. In the first part, I'll introduce some of the concepts and challenges around dataset harmonization, search and analysis, and I'll show you briefly a reference architecture that helps to address some of these challenges. I'll try and keep my part of the talk to under 20 minutes so that we can quickly get to part two when Dr. Kashout is going to tell us about the recently launched AHA Precision Medicine platform. He'll tell us why this platform is important and how it applies the concepts of harmonization, search, and analysis to ultimately help save people's lives. Okay, I am having clicker challenges here. Okay. One more. Here we go. All right, get there at last. All right, so here's what I plan to talk about in part one, with three concepts that apply to the AHA Precision Medicine platform, and I think they also apply to any platform that aims to enable research across multiple data sets. First is harmonization. I'll try and explain to you what that means, why you might need to do it, and how you can achieve it cost-effectively at any scale. And then search. Before you can know what data sets will be useful, you'll need to have a way to see what's inside them. We'll talk about how you can build a search index, and I'll show you an example of a search and discovery web page that you can use to search for data across many data sets. And then analysis. Once you've searched and found data sets with data that you care about, you'll want to dig deeper into those data sets to discover patterns and correlations, possible causes and effects. You'll want to access the latest and greatest in data science and business intelligence tools, and you'll want a way to capture and share your insights. And of course, you'll want to do all of this on AWS and take advantage of the speed and scalability and cost effectiveness and access to the latest in technology. And I should also mention at this point that at the end, I'm going to point you to a blog post that comes with a sample application, so that if you do hopefully find yourselves curious to learn more, then you'll have the opportunity to dig deeper and explore these things for yourselves. Okay, there's got to be a better way. So it's the, Let's see, does the keyboard work? Yeah, that works. Okay, thank you, Taha. All right, so let's set up a hypothetical scenario. Imagine you're a researcher. It doesn't really matter what kind of researcher, but what does matter is that you've come up with a hypothesis. It's an exciting hypothesis, one that you think could have a big impact if it can be proven. What you need now is data, lots of it, to see if your hypothesis holds. The data, of course, must contain the information fields that you need and should ideally span multiple jurisdictions, timeframes, and demographics to see if your hypothesis is widely applicable. You suspect that there are lots of potentially relevant data sets out there, and sure enough, you find many data sets, but the problem you quickly encounter is that they don't conform to any common standard. Because they were created by different people at different times, often for different purposes, they can use different names to mean the same thing, and different names, the same name to mean different things. They can use different units of measurement and different scales. Some values can be represented as continuous variables, while others use discrete categories. And even when categories are used, their values might not align across the datasets. Instrument or sensor readings can be skewed from dataset to dataset because different instruments were used, which may have been calibrated differently. These issues make it very hard for you to filter and combine the data across the different datasets or to do any sort of meaningful analysis across the superset of the data. Each dataset might be fine on its own, but they don't work well together. They are discordant. So you need to make your datasets play nice together, minimize the conflicting standards. You need to harmonize them. You focus on the information that the datasets have in common that you care about, and you convert this information to a common standard if possible. Harmonization can be a lot easier said than done. Sometimes it's easy, like giving a variable a standard name, and sometimes it's impossible, like when key information fields are missing and can't be imputed. Sometimes it's possible, but you'll lose fidelity of the data, like when you try to align continuous with categorized variables. And sometimes it's possible, but complicated, like when you try to align readings from differently calibrated instruments. Often, harmonization is an iterative process. Look for the 80-20 rule and find a handful of variables that, when aligned, will give you most value for the least cost, and then iterate. Decisions need to be made dataset by dataset, variable by variable. You need to make trade-offs with your researchers' goals in mind. It's not always easy, which is why we love our statisticians and data scientists, but our goal is to provide a great platform to help these good folks do their job. So here is our recommended approach. Start by storing your raw source datasets in S3. S3 allows you to secure your data through encryption and access policies, and once your datasets are in S3, you can do all sorts of cool things with it. We're also going to store the harmonized version of each dataset in S3 once we've completed the harmonization process. You'll want to code your harmonization processes in Python or R. These languages are de facto standards for data exploration and manipulation, and they're very familiar to data scientists. And there are huge communities where you can get help for many common problems. And Jupyter Notebooks is a very nice open source web application for integrating your documentation, your exploratory analysis, and your harmonization code into self-contained notebook artifacts. And you can share these notebooks with the researchers who are going to consume your harmonized data. In fact, you can even publish the notebook itself in S3 along with the harmonized data sets that it generates. This will unambiguously define how the harmonization was done in a way that anybody can review and reproduce for themselves. Apache Spark is a fast in-memory distributed compute engine that lets you easily scale your data and compute workload across clusters of multiple nodes. Spark can be programmed easily with Python and with R, and it gives you access to a rich set of data manipulation and machine learning libraries, which makes it a great platform to address the full gamut of harmonization challenges. And Amazon EMR provides clusters in the cloud that can run Apache Spark. The clusters can be sized to handle the compute workload for whatever size and number of data sets you need to harmonize. Spark running on EMR clusters can easily access the source data sets that we've stored in S3. Your harmonization code should also save its output, the harmonized version of those data sets, to S3 as well for researchers to later access and analyze. So now that your data sets have variables that are called the same thing and that mean the same thing, you'll want to make them easily searchable. You and other researchers need to be able to find the data that are relevant to your hypothesis. So spin up an Amazon Elasticsearch cluster. With a few more lines of code in your harmonization notebook, you can easily save the harmonized data that you want to search on to an index in the Elasticsearch cluster. And you can build a web search UI similar to the one that was shown here from our sample app that will let you filter on the harmonized variables. In our sample, we included an embedded dashboard to let you display some aggregate information on the filtered data. This lets you do a preliminary analysis across all the data sets and help you assess which data sets have data that's relevant to your hypothesis. One nice touch is to include an HTML link to the harmonization notebook right here in the search UI. This lets your users easily click on the link to see the Harmonization notebook, and they can see how the harmonization was done and verify that it suits their needs. Okay, so using the search capability, we have now located several harmonized data sets that you want to analyze to prove or refute your exciting hypothesis. What tools can you use? Well, one great option is to reuse the same tools that we recommended for doing harmonization, for all the same reasons. Python and R with Apache Spark running on EMR clusters gives you access to many of the latest open source data analytics, stats, and machine learning tools. You can spin up data science workspaces on AWS with all these tools pre-installed. You can make it as small or as big as you need it to be, depending on the combined size of your data sets and the kinds of analysis you want to run. And you pay only for what you use. You can even take advantage of low-cost spot instances. All your data sets stay safely stored in S3. This separation of storage and compute gives you the flexibility to size and resize your compute cluster as you need. And it also means you can shut down your EMR cluster when your analysis jobs are done, and you won't lose your data. As we discussed when we talked about harmonization, you can use notebooks to encapsulate your analysis code with its output to create beautiful, live, executable, and reproducible scientific artifacts that you can easily share with others. Here's an alternative way for doing your analysis. Attractive if you're more comfortable with relational databases and BI tools than with data science and programming. The Amazon Athena service lets you define relational database tables to describe your data, which stays stored in S3. Your harmonization notebook can be made to automatically define Athena tables for you, so that when your harmonization is done, you can immediately start running SQL queries on the Athena console, or from SQL clients or BI tools such as Tableau. Athena is one of our serverless services, which means it's just always available. You don't have to worry about sizing clusters or anything like that, and you pay only for the queries you run. And speaking of serverless services, you'll also want to try out Amazon QuickSight. QuickSight is our business analytics service. It's compatible with a wide variety of data sources, including Athena. This means that within minutes, you can connect QuickSight to your data sets in S3 via Athena and create beautiful charts and tables to reveal patterns and relationships in the data. QuickSight includes an in-memory calculation engine called Spice. Spice lets you build really fast interactive visualizations and dashboards. And with QuickSight, you can create stories that allow you to reveal your insights in a logical progression. Interactive storyboards and dashboards can easily be shared with others in your organization. So we've talked about why and how you can harmonize, search, and analyze your data sets on AWS. Let's take a quick look at how we can pull these steps together into a complete architecture. Starting with harmonization. The harmonization process is executed on an Amazon EMR cluster running in your VPC. The cluster has Apache Spark and Jupyter installed, so that once it's running, you can securely connect to the Jupyter Notebook server from your web browser and start creating and running harmonization notebooks. Your harmonization code reads the source data sets from S3, transforms the variables and values as needed, and writes the harmonized versions of your data set back into S3. When you're done harmonizing, you can download and save your notebooks in your source code management system, and then you can terminate the EMR cluster. There's no sense paying for it when you're not using it, and you can always spin up another cluster when you need to run harmonization again. To add a search and discovery portal for your data sets, create an Amazon Elasticsearch domain. Use the harmonization process to index the data that you want to make searchable. Elasticsearch has a connector for Apache Spark that makes it really easy to efficiently bulk save the data that we want to search directly from the harmonization notebook. To create a web UI search page, we can host the required components as Docker containers in the Amazon ECS service. The UI should be deployed across 2 availability zones in your VPC to ensure fault tolerance. An application load balancer can be used to provide a single URL entry point. And you can run the search UI as a standalone site or integrate it into your existing website. Add Athena and QuickSight to the architecture to provide the ability to create and share analysis of your data sets. There are no servers to deploy. Just log into the console and start querying. Or, as I mentioned earlier, you can reuse the EMR cluster with Spark and Jupyter Notebooks to do your research and analysis, leveraging the latest and greatest in open source data science tools and the power of programming in Python or in R. A couple of final points in this architecture. It's S3-centric. We can securely store multiple versions of your data sets in S3, and EMR can easily access your source data sets in S3, as can Athena and QuickSight and many other services. S3 is our source of truth, our data lake. Data lake-centric architectures can be very powerful. They let you tap into your data from a wide variety of specialized tools and services that you can deploy as and when needed. I definitely recommend you look into data lake architectures if you haven't done so already. Is this the only way to align and combine discordant data sets? Probably not. I'm sure there are other approaches. Maybe you'll come up with some new tools and new techniques and opportunities to leverage new AWS services like Glue or Redshift Spectrum and more to improve on this reference architecture. That would be great. Hopefully the reference will get you started, though, and give you a framework for thinking about your approach. So I've skimmed a lot of topics just now. As I mentioned at the beginning, if you're interested in digging deeper, you should check out our AWS Big Data blog on this topic. The blog comes with a companion sample application. Clicking the Launch Stack icon fires off CloudFormation templates that will create the entire reference architecture in your account, ready for you to try out. The blog uses publicly available police incidents data sets from several US cities to allow you to try out all of these concepts that we've just discussed. All the code is available on GitHub, so dig as deep as you like and reuse as much of it as you see fit. And you can find the blog post online by searching for the keywords Harmonize, Search, Analyze, AWS. So here are the main points to remember. To find and analyze data that spans multiple data sets, you first need to harmonize them. Create variables that are called the same thing, that mean the same thing, and whose values can be meaningfully combined and compared. Provide a search page that allow researchers to apply filters to find data sets that have records that they want to use for their analysis. The search UI should also include a dashboard to enable some preliminary analysis of the combined data. Analyze the data sets using the latest in data science and/or business intelligence tools, and create rich documents to share your insights with the world. Prove your exciting hypothesis and advance the frontiers of science. And of course, do it all on AWS. Securely store your data sets on S3, build out a data lake strategy. Take advantage of the fact that you can spin up an entire environment in a matter of minutes to experiment and quickly try new techniques to get to your discoveries faster. Okay, I'm relieved to tell you that's the end of part one. We'll hopefully have time for a few questions at the end, but now it's my turn to relax and hand over here to Dr. Taha Kashout, who's going to tell us about the precision medicine platform. Thank you, Taha.
Thank you very much, everybody. Really appreciate it. Thank you, Bob. Again, I mean, this is really collaborative effort between the American Heart Association, Amazon Web Services, working hand in hand over the last year just to kind of produce this really awesome platform, which I'll describe in a bit. Also, a technology partner to Amazon, working under the direction of American Heart Association, Rain Cloud, members of which are all here in the audience. But first, I want to talk about, the general context. What is precision medicine, and why that's so important? I mean, perhaps if you look at one of the most exciting discoveries in the 20th and 21st century has been the human genome sequencing. And the evolution of that, especially over the last 2 decades, about how not only the cost is getting lower, but also our understanding about the human body is getting far better resolution and trying to understand how the correlation of these different things can come together. So in a sense, we have an opportunity in front of us, really redefine diseases as we know them. Cardiovascular disease continue to be the #1 threat worldwide, and the cost of that, I mean, edging around $1 trillion by 2035. Every 2 seconds, someone around the world will die from cardiovascular disease. But the upside of this, the good news about this, most of cardiovascular illnesses are preventable. If you understand your environment better, if you understand certain stressors, if you understand the diet and lifestyle, if you can understand also now new risks that we're learning about for the first time, such as your human genome, certain variants within your genome that can contribute to certain risk. Why certain people need double the dose of blood thinner, for example, before they can have the same effect of that drug on their body, or why certain people are more at risk of AFib, atrial fibrillation, that's a high risk of stroke and other things, than others in the community. How your zip code can contribute more to your health condition than your DNA. I refer to that as your ZNA as opposed to the DNA. So it's a fairly complex, topic, but really at the crux of all this is really relies about can we get and to index all this information about the human body and be able to present it in a cohesive way so data scientists can start taking us to that next level. But as you can imagine, I mean, there's a lot of challenges to acquire the data in the first place. As Bob was mentioned, how you even harmonize it and make it available later on. If you don't believe me, just try to get your medical record from your healthcare provider. I mean, and you'll get an idea now, how can you get one institution to share their data, which is their sort of incentive to continue publishing with another institution. This is really where the beauty about where American Heart Association comes to play. But first, I want to mention that outside the National Institutes of Health, the NIH, American Heart Association is the leading funder of research in cardiovascular, since 1949. I mean, lots of grants, lots of guidelines, organizing communities around understanding their health risks and behavioral changes and ways about how you can contribute to your health. And funding data science. I mean, before data science was sexy. So it's really amazing to see how American Heart Association really taken this to heart to bring the next evolution of data science to help prevent cardiovascular diseases and stroke. So let me start first about, back to Bob's comment, how you integrate all these information. So American Heart Association is really, the aspiration here is taking this really seriously about can we index and provide a unified virtual place for all the data around cardiovascular and stroke, and be able to build a community, a large community of data science, researchers, entrepreneurs to come and help us better understand the meaning of this data and advance the research behind for cardiovascular research and stroke. To start with this, the American Heart Association established the Precision Medicine Institute. Dr. Jen Hall is the chief of that, and start building the precision medicine platform. Working with government agencies, working with pharma, working with academic institutions, large data aggregators, as well as healthcare the institutions and consumers, about how can we provide you with sort of the notion about a cloud within a cloud to be incentivized to come to one place, conduct your research, and then be incentivized to share those results with the rest of the community so you can have wider collaboration. But as you can understand, every time we bring one of these partners that have these data sets and have to work with them about providing these data sets available, I mean, it's a fairly complex topic from relationships to regulations to technology to the data to understanding really what the data means and whatnot. So really look at this as more of a holistic view where the American Heart Association is more as an honest broker about bringing this together while making sure that the data that you own will always be secure within your control, but provide you with also a shared environment where this can help elevate the discussion to the next level. Data right now, Institute is really trying to focus on, ranges from anything from personal information, so an individual, about the individual, from their wearables to their electronic medical records, et cetera, to things that are more of a cohort, like large cohorts been running for decades. Large genome-wide association studies have been done. How can you bring those to the fold? Clinical trials done by pharma or large academic institutions, how can you also bring those forward? And also understand about the environment, environmental risks, behavioral risks, guidelines that the Institute has been working on, and registries, and how you can all bring all those together in one fold. So it's fairly complex challenge. However, there's the elegant design that the team here has been working on, really can provide sort of the vision for the next way of handling these kind of data. And this is where the Institute, Amazon Web Services, and partners come together. So let me introduce you now to the Precision Heart, or the Precision Medicine platform under American Heart Association. I mean, you can go right now, precision.heart.org, register for an account to browse the information, and then go beyond that. This went live in a open beta March 15 of this year, with the goal to go public beta by middle of July. And let me walk you through some of the features that will be available. And again, it's still within the same reference architecture that Bob describes around the Harmonize, search and analyze. But we also added another dimension to that, which is the community. The community that AHA funds, the community that, and issue grants to, the community that AHA works with, from governments, academics, entrepreneurs, data scientists around the world, bringing all those together around that platform, so that way we can advance the knowledge, but also see where we can take this to the next level. The national scheme about also, like, how can researchers learn from each other? By sharing some of those components. It could be sharing their methods, it could be sharing their data set, it could be sharing their results, and then how they arrived at doing this. So the AHA has worked quite a bit on establishing also a community attached to this platform. So it's not just a dump of data, you go to precision.heart.org, but actually an ecosystem with tools and researchers and other things that are focused on cardiovascular and stroke. So when you land on the precision.heart.org, after you log in, this is again back to the reference design that Bob was mentioning. And the first thing is this harmonization scheme, so like the 80-20 rule. How can I provide you with a quick search that can go across wide variety of data set that vary in structure, vary in content, vary in context, have been collected over time, from population level data to individual level data, from observations and clinical to genomics. It's quite complex to put all that within one framework or one design, but this elegant design here really is the first thing you come out. It's like, I might be just looking for, let's just say, this age group and that age group, and that automatically, with the harmonizations being done on all these data sets available, try to narrow down your search, and then you might say, well, I want to look for females in this particular cohort. So basically, you're building your own cohort from so many other cohorts, and show me the ones that ended up with, for example, a stroke or cardiovascular event. So these are what these pie charts help you to narrow down sort of the selection, which I'll show in the next screen. And then the accordion on the left, this is really where Bob also mentioned too. If you want to further filter this down, for example, I want to show the associate. I have a question or interest about perhaps the association of a particular gene or particular mutation with cardiovascular risk, or maybe an outcome such as MI, heart attack, or maybe stroke. Can I examine that also on this population? Can you further filter down the results so I can find that particular gene or records associated with that particular gene? So first thing is those pie charts. This is really more of the harmonization sort of variables across all the data sets. The data sets that are currently available, as I mentioned, they vary from cohort to individual to from genome and clinical observation, et cetera. And then you have the filter on the left to further down the results, so you can build your own cohort. These data sets, the majority of them right now are publicly available, but also the Institute is working with pharma and others to provide other data sets that can be available, where you could request from one place access directly from the owner of that particular data. And again, goes back to this cloud within cloud sort of concept. So protect the privacy and security of the information of the data owner, and then they will control who they want to share that data with, where AHA is really more of a conduit or the trusted factor that can help that handshake. So researchers don't have to go 20 different places, ask for different kind of agreements, and try to download that data, and guess what? The site is down, or it's not documented, and then still have the onus of going and further harmonize that data. So you can answer just a simple query, show me the risk of statin in certain population. Is there something available to me that can be correlated with another outcome? So this is one scenario. For example, here we harmonized, here we search on harmonized data across disease outcome with gender, and as well as a risk factor. So you can imagine now the data sets that we have, about a dozen or so now, we're down to about one data set that meets that, especially when you added the filter on the left. Show me that had cardiovascular disease, hypertension, and show me also that I'm looking for one particular gene, the KRAS gene, that has, in my theory or my study, that might be associated with the higher cardiovascular illness. And you can imagine not only that the data sets have been further selected, but also the number of records within those data sets that match that query are also identified for you. And then you can see here is we have the Jupyter node that Bob was mentioning, is how now the owner of that data set was made the harmonization scheme. So now I can further learn from that institution or individual how they went about it. For example, that figure over there is show me the correlation between high cholesterol and your body weight or a BMI, and show me like like I'm just trying to test that one hypothesis. But not only you can see the results, you can share that results with others, and you can also share the code that went into it about how you conducted the analysis, as well as you can see at the bottom there the harmonization, how these variables across the different data sets were matched and sort of harmonized and made available. And you can further challenge this or say, I can do it better, or maybe you can learn from it, or you can just take this work and maybe add your own data set to further harmonize that. Now, if it happened that this particular data set is owned by someone that requires a license or requires some knowledge upfront about utility of the data before you can use it, right on there from the platform you can request access to that data set, and this is where the handshakes start between the researcher and the institution. Here's another sample about, now let's just say now I want to take this data set and further enhance on it. This is where the institute provides you with a researcher area or a workspace, so where you have computation, you have access to a number of tools, statistical tools and machine learning, and what have you. Also, you can publish your own notebooks in your own private area and work on the research. And also, like one of the nice features that we enabled for the March launch is you can bring also your own data set to this platform, as long as you adhere to the terms and conditions under institution, and it's up to you how you can further enhance this. And so really, again, an honest attempt by American Heart Association to change the incentive about sharing publication, about sharing evidence. How can every individual in the community will be able to contribute to this, in addition to the larger effort that AHA is trying to bring these data sets. Now, you as a researcher can also bring your data and further explore on the platform. The Learn section is really one of the most exciting place over here. So we launched in March. Prior to the launch, we're working with a few data scientists around, from the cardiovascular and stroke community, just to kind of test out the platforms and whatnot, and start helping sharing some of the content. Since the launch, these are some of the examples that the community has been able to share widely with others. I mean, this can be anything, like I just, generate, here's a script how you can do, let's say, some kind of regression of variable A against variable B, or I was able to publish this research and here how I've done it, maybe you can enhance on it. Sometimes others can come and fork this and further say, oh, you've done this in R, let me show you how it can be done machine learning on Spark, for example. I mean, it's a really lively community about sharing lessons learned and whatnot. But ultimately, what we want to really come to is if you have generated new evidence, here's your chance to back it up all the way, not only just the data, but also the methods and how you went about it. And then you can also reference the work in your own peer-reviewed publications and whatnot. Here's a number also of, so as Bob mentioned, we have the Jupyter Notes kernel, and researchers don't have to learn anything about, AWS or S3 or EMR or whatnot. They can just code in their own language. So right off the bat, you can code in Python or you can code in R, but there are a number of other also languages you can code with. But also we prime the platform with a number of statistical tools and genome sequencing and analysis tools. With over 80 plus now apps, different apps you can bring. And if you code in Python, you can also work with the team and they'll help you really bring those libraries and whatnot onto the platform. And there's a website, if you go to precision.hard.org, you can always see like what is the latest, or engage with the community and request different things to be added as well. Here's the number of Python packages. And the great thing about Python already comes in with a very rich, well-validated data science tools for machine learning and statistical analysis and whatnot. So that advantage already carries forward on the platform, but you can also bring your own as well. And lastly, I want to talk about the community a little bit. So one thing, I mean, it's still in beta, but we wanted to allow this forum discussion, basically. I mean, this can be about, like, how can I add my data set? Or I discovered a novel discovery over here about this kind of association between a risk factor and the disease and maybe a variation in a human genome. Is anybody else want to work with me on this? Or has anybody experienced this, whatnot? And this is really the whole idea about this Stack Exchange forum that is tied very directly to the platform. Since the launch in a couple of months, we have about 81 followers and growing. This is still, again, in test mode right now. AHA is also trying to engage with the community through social media with the hashtag right now, AHA Precision. But you can see also the hockey stick of people that are registered on the platform. Currently, we have over 400 members that register with the platform. About a couple of dozen of those now have access to workspaces and research. They're actually using the cloud resources to conduct different kind of research, do harmonization on their own, do some machine learning on their own, share it back with the community. So, and the hope is by next month when this goes public beta is we have set sort of the stone and tested the platform and everything so we can take this to the next level. And don't forget about like bringing your own data set to the platform because that's just as important as everything else that we're trying to do over here. And happy to answer questions next. Bob.
David Michaels, DNA Nexus. Precision FDA was a very successful program. What lessons learned from there to bring it over to American Heart Association?
That's a really great question. So Precision FDA is, it's almost like regulating genomic tests in the marketplace by a robot. The idea there with Precision FDA was really just to build the evidence. How can we build the evidence around one particular niche, which is how accurate are the tests that are on the marketplace right now and issue challenges, whatnot. So in the same spirit, this takes it further along because here really we're generating new evidence, clinical evidence, engaging a wide array from researchers and focus on cardiovascular and stroke. So definitely we'll build on things like Precision FDA, but I hope this will be even far more reaching in the community and beyond that niche about genetic tests. We're looking at observation studies, genome, we're looking at all sort of different aspects and whatnot. Bob. Thank you.
Any other question over here?
I mean, that's really the hope, is to have wider collaboration around this in a way that people are willing to share their results. So Again, the challenge, as I mentioned, is contributing data in a way that people are not mistreating your information and whatnot. So baby steps, the Institute is working with certain consortia around stroke and around cardiovascular, trying to respect how we can generate that evidence. And as we go along, we want to give the autonomy for researchers to do new discoveries. And that's really where the beauty lies. So think about this as more of an extension of GWAS sort of approach, with the hope that you can continue generating new evidence.
Any other questions? All good. I guess we're wrapping up a little bit early. All right, thank you very much, everybody.